Okay. Silent movie. No, that's okay. We have everything else already recorded. It's okay. We got about 40 people here, so I think the collective memory of 40 people is accurate enough.
Obviously, that is not. Obviously, that's not.
That's not the case. All right. So, any other questions?
When you said like when you were comparing to like the A to A, you said already the CMP. Then you use go to CMP B for 1 byte.
Well, that is something for you to answer because I intentionally left that out because that can lead to problems if you use the wrong one. So you have to think about how many bytes am I actually comparing.
If it's 1, can you still use compare long? Would that be wrong?
Okay, the question is, if I only need to compare 1 byte, but I choose to use compare long, will it be wrong? What do you guys think? I will make you guys work, but I'm the one who is taking the paycheck home. Okay, so I'll repeat that question. The question was, if I am supposed to compare a byte with a constant, okay, but I'm using compare long instead, is it wrong? That's the question. Now that is a really tricky question. It's a tricky question because it depends on a number of factors. Yes? Say again? Well, let's say we are only reading in 1 byte at a time. So we are still preserving the logic of this program as well as your homework assignment. Okay? So assuming that we are reading in 1 byte at a time, we are comparing long instead of comparing byte. Would it be wrong? That's the question. Okay? It depends on a number of factors. Go ahead.
Wouldn't it depend what's in the other 3 bytes?
Exactly. The question is, what is in the other 3 bytes? Because when you compare long, you are comparing 4 bytes. Okay? The byte that you specify is the least significant byte, which is fine. Okay? You got the right location for that 1 byte. Now the question is, what else is there? Okay? In other words, what are the other 3 bytes? After that 1 byte that you intend to compare. If those 3 bytes turn out to be 0, then you're okay, because those zeros becomes leading zeros of the 32-bit number, which does not change the value that you're actually comparing. If those 3 bytes turn out to be non-zeros, then you have a big problem, because now you're comparing a ASCII code, which is from 0 to 127, to a number that is much larger, because the more significant bytes are non-zeros. So is that answering your question?
Yes.
Okay. It's not a straight answer because it's not a straight question to begin with.
Nothing in computers is a straight anything. Computers aren't straight at all.
Oh, it is straight. It's our interpretation that is not.
Yes.
Because we made assumptions. That is the problem. Because when we come from a C class, we make certain assumptions that is no longer valid in this class. All right. So any other questions? If there are no other questions, well, the recording is still there, even though the first part does not have the audio part. But
You did that in Android.
I did, yeah.
Last year, around this time, there was a lecture that covers sort of what you covered today, and that's that.
Oh yeah, absolutely.
It's a salad.
And then the year before that.
You do about once a semester at least.
I do not do that on purpose. If I want to do something on purpose, I would forget to do it on purpose too. So in order for something to happen, it's not something that was intentional to begin
You
with.
do it about once a semester at least.
Yeah. It's the timing that seems to suggest it was intentional. It's not one of those days where I have to talk about Microsoft and whatnot. Then it's always recorded, right? The audio is always on for some reason.
Yeah. Happy
All right.
apocalypse, by the way.
So now that we got the homework, squared away, we will go ahead and continue with the next topic. The next topic is how to use the system stack. Okay. Now this is, I would say, in many ways more important than file I/O. Okay. file I/O is really a matter of reading the specification. What does EAX mean when we have a system service call? Okay, and then what other registers need to be initialized and what are they used for? And that's about it. Okay, for system services. But in terms of the stack, it is an entirely different concept. So we'll go take a look at the system stack. And this is also where I think it will be helpful for you guys to read the notes a little bit ahead of time, because these concepts do take time to sink in, especially when we get to the later portion of the stack concept. So let me show you where we are at this point. We are now in topic 7, and we are going to talk about the stack calling, returning. We'll talk about how to use the make program, okay, the make utility program, which is really interesting. If you know how to use it, it can save you a tremendous amount of time. We'll talk about how to use the stack in assembly language programming. So these are the topics that we'll go over at this point. And then after this, we'll start to get into much more interesting stuff, which is about the call frame. Okay, at some point we'll be able to look at C subroutines and then translate C subroutines into assembly, and then we'll have our assembly code to call C subroutines and back. Okay, we'll have interoperability between C code and assembly code. So that will be the kind of the cool part of this class. So, but in order to get there, the first thing we need to know is what is the system stack, what is the stack pointer, and what instructions we can use, what can we do with the stack, regarding the system stack itself. Okay, so where we are at this point is in topic 7, and we are going to talk about the stack. All right. Did you guys talk about the stack in C and C++?
No.
Yes.
Okay, have a mixed answers here. Okay, for people who answered no, did they even talk about the term stack at all?
Yes.
Yes? Okay. And in short, what is a stack? What makes a stack a stack? As opposed to a stash of something.
You can only
Sorry.
retrieve the
Couldn't
thing
resist.
that was put into it last.
It's the ordering of putting items into it and the order of getting things out of it. Okay? So with a stack, what is the order of putting things in and getting things out of it? Last in, first out. Okay, LIFO. Okay, as opposed to what is the other way? If you go to Walmart and they want to say, okay, you know what? The way we serve customers is last in, first out, and you turn out to be the first customer who lined up at the counter before they even open. Would you be happy about that arrangement?
No.
Okay, so we do understand what is last in, first out, okay? Because last in, first out means the last thing that get into the line or the storage is the first thing that you retrieve. Classic example of last in, first out, U-Haul truck. Okay, I'm pretty sure most people have the experience of either moving your own stuff, from one apartment to the next, or helping someone to move, their apartment and their other stuff, from one place to another place. Okay. So let's say that you put a map or the address of the destination into the truck first. Okay. You're thinking, okay, I got to make sure that I bring the map so that I know where I'm supposed to drive the U-Haul truck to, and then you put it into the truck first, and then you stash all the other stuff in, and then you push the last bicycle on the truck, and then you slam the tailgate down. Okay? And then you get into the driver's seat, and then what do?
You have no clue where you're going.
you have no idea where you're going. And then how can you get back to the address?
Load porch.
Everything else. Yep, exactly. Or you can find a really big slope, and then turn your truck like this, and then quickly accelerate with the tailgate open. That will dump everything out pretty quickly, and you can get to your map. Because it's last in, first out, right? The very first thing that you put into the truck is the last thing that you can get out of the truck. Okay, so that's last in, first out. Now, instead of using assembly code to talk about last in, first out, I can do this in C and C++. Okay, so that's the one thing that we're going to do is to use C++ to basically say what are we going to do with a stack, but only using C pointers and stuff like that. Okay. All right. So let's use a text editor here. And where's my text editor? Under accessories, mousepad. There we go. Okay. Now, the thing about a stack, especially when it's implemented in assembly, is it grows downwards. Okay. Okay. So we'll basically say, a stack pointer. A stack pointer, as the name implies, is a pointer. So now the question is, where does it point to? Okay, where is a stack pointer pointing to? By definition, at least in assembly language, it points to the very last thing that you put on the stack. It points to the lowest byte of whatever you push on the stack. The last thing that you push on the stack. So let me just write it down so that we have a reference. Okay? It points to the lowest byte of the last item pushed. And the word push in this case is specific because a push operation and pop operation are specific to stack operations. Pushing basically means stored, same thing. Okay, so pushing is to store, popping is to retrieve. Okay, all right. So that's the definition of a stack pointer. It's just a pointer pointing to the lowest byte of the last item that you push. Okay, so that means, would that mean an empty stack has a stack pointer pointing to high address locations or low memory locations?
Low.
High. Okay? Because as we put more items on the stack pointer goes lower. Well, this instruction or this description itself does not indicate which way it grows. So it was just a step, okay? So you guys got your guess, but here's the answer, okay? Initially, the stack pointer points to the highest, okay, I should say, points to 1 byte past the last location allocated to the stack. Okay. All right. So what do we do when we push, let's say, a 32-bit integer? Okay. So let's take a look at what we do when we push an integer. And in this case, instead of using SP for stack pointer, we're going to use ESP because ESP is the actual name of the stack pointer for the x86 instruction set. So we're going to use ESP instead of just stack pointer here. To push an integer, I'll just call it I here, on the stack, the equivalency instruction is going to be like this. Okay. Don't copy anything yet, I'm still thinking. Processing. There we go, that's the correct one. Okay. That's the C equivalent instruction of how to use a stack pointer. In this case, what is the type of a stack pointer? It's a trick question. It's a void pointer, that's right, because a ESP as a stack pointer has no types associated with it. It's just a pointer. It just says, I store the address of something. That's it. So when you look at the type of a stack pointer, the best way to look at it is a void pointer, which means the stack pointer itself does not tell you whether it's pointing to a byte, to a 16-bit integer, or a 32-bit integer, or a struct. It just says, I'm pointing somewhere. But since the i386 instruction set is byte addressable, it is always pointing at least to a byte. Okay, so each location corresponds to a byte. But we don't know how many bytes go together, as one thing. Okay, the stack pointer cannot tell you that. All right. So if you look at the C code here, which starts with an asterisk, open paren, minus, minus, in x asterisk, in parentheses, ESP, close parenthesis. What does it really mean? I'm missing one pair of parentheses, that can help your interpretation of this, C statement. But with this one, I'm hoping that things get a little bit more easier to understand. Okay. So how do you read something like this in C? Well, you work your way out from the innermost parentheses. Okay, just like when you read anything that involves parentheses or square brackets. All right, the innermost is int asterisk, which means it's a typecast to a integer pointer. Is that okay? So let me just highlight which part I'm talking about here. I am talking about this part here. In other words, this entire thing is a typecast operator in C. It is basically just saying, I'm casting whatever is to my right-hand side to become an integer pointer. From whatever pointer it is, or even an integer, now it is an integer pointer. Okay? What am I casting? What is being turned into an integer pointer?
The void pointer.
The void ESP. Okay? ESP is now casting into an integer pointer. What happens when you have a decrement of a ESP of an integer pointer? How many bytes is actually going to be offset by?
8?
1 byte.
Well, assuming an integer is only 32-bit. 4, that's right. Okay, so this will basically change the stack pointer itself by 4 locations, and 1 location is a byte. Is that okay so far? That is all C code. Okay, this is only C code. I'm not putting in anything other than basic C code. Okay. And is this a pre-increment operation or post-increment operation? In other words, as an entire expression, am I referring to the value of ESP before or after the decrement? Before or after it is changed? After. It's a pre-increment operation. That means it's pre-decrement, which means the value of the entire expression is the value after the decrement. After the decrement operation. We do a subtract first, and then we do the operation. Yeah. Okay. And then what is the outermost? Yep. Go ahead.
Why do you use 2 minuses, not 1? We're going to store 1 integer.
Because if you have 1, it is a negation. 2 is auto decrement. Yep. And then the outermost operation is the asterisk. What does that mean? Dereference, okay, and what does dereference do?
Allows you to put an value into a pointer location.
Yep, it basically says whatever to my right-hand side, I will treat it as an address. And I'm not interested in the address, I'm interested in what is at that address. So in this case, because this expression is on the left-hand side of an assignment, it means I'm storing whatever value is on the right-hand side to that memory location. Are we still doing okay so far with this instruction here? How do we do this in assembly?
Easier.
Well, okay. Let me quote unquote cast my question, into another form. Do you think the assembly version of this code is going to be complicated or easy?
Easier.
Do we know enough instructions to implement it here at this point?
Yes.
Okay, so let's take a look. I'm going to throw out something here just so that you can choose from those instructions. Okay, so we have talked about move instruction. We have talked about the add instruction. We have talked about that. We have talked about move instruction. Okay. Let's see here. We got 1, 2, 6. Yeah, we got move instructions and we got add instructions. So now the question is, how do we combine these instructions, and what do we specify as operands in order to complete the implementation of that line of C code? Where do we start? I'm not too concerned about the I. I'm not too worried about the I. Okay, I'm more worried about on this side here. The I part is easy, okay? If you really want to get the I out of the way, fine, we'll put it into a register. Fine. So the right-hand side is now done, okay? It's in the register. My current concern is now the left-hand side. What do we do with the left-hand side? What do we need to do first?
Decrement.
Okay, the first operation in the C code is typecast to integer pointer. What do we do in assembly to do a typecast?
Nice.
That's a very tricky question.
We don't count.
Extremely tricky question.
Nice.
So tricky that has a trivial answer. We do not do anything. Because assembly code has no types. Okay, so when we have a typecast operation, there's nothing you have to do. Okay, so the typecast operation, this part here, there's nothing to do. So the next thing we have to do is to do the auto decrement. How do we do an auto decrement in assembly code? And remember, you can only choose from these instructions. You cannot use subtract long. Can we use add long to do what subtract long is supposed to do?
-1 to the register.
Not -1.
Or add 1.
Negative.
Not 1.
-4.
-4.
Yeah.
Okay, so we have to add long $-4 because we are not going to location -4 to retrieve the value to subtract. We are subtracting literally the value of -4. What are we subtracting -4 from? ESP. How do we translate ESP into assembly? Percent ESP, because it is one of the registers. Okay. All right. Now that we have do all the calculations, this is the magical moment because I gave you 3 instructions: 2 move L and 1 add long. I have already used up 1 move long, 1 add long. I only have 1 move long instruction left. What do I do here? I know what I'm moving from. I know, this is EAX. What about the other side?
ESP.
ESP, but not just ESP, not dollar.
Percent.
Well, that's percent ESP, but there's something around it also. Parentheses, because we are not copying the content of EAX to ESP. We're copying EAX to where ESP is pointing to. Okay, so this is an indirect operation. So that means that is what we need to do. Okay, 3 instructions corresponding to that one single thing that we specify in C. Is that okay? What if I tell you that we can do it in one single instruction instead?
Direct index.
That would do the same thing. Well, it will do the same thing, but only if there is a push instruction. Okay? Why do you think I said only if there is a push instruction?
Because there is for x86, but there might not be on other platforms.
Exactly, because on a RISC processor, they may not give you a push instruction. Because if I can do this using regular move and arithmetic instructions, it means there's no need for the push instruction that actually does pretty much the same thing. Okay, so that's why on RISC architectures, such as the ARM architecture, the MIPS architecture, and the PowerPC architecture, I'm not 100% sure, but they may not give you a push instruction at all, because it can be implemented using a combination of other instructions. Okay. All right. So this is push. What do you think we have to do in order to retrieve an item from a stack? Pretty much the reverse of this. And when I say the reverse of this, I really mean literally the reverse of that. Not just spelling everything backwards, but also turning the meaning of everything backwards. Okay? Auto decrement becomes auto increment. Pre-decrement becomes post-increment. Okay? And then the right-hand side and the left-hand side, obviously, they also have the reverse. In other words, to pop an integer I from the stack, okay, to pop an integer from the stack, we have to do this in C. I want to pop it into I, okay? So we basically say I is, retrieving something from the stack. So just by saying that, I know that I'm retrieving something that is pointed to by a pointer. The question is, where? Okay. We also know that I itself is an integer pointer, so I know that I have to cast ESP into an integer pointer in order to do something. I'm going to group these two into one. So the question now is, well, what am I going to do to adjust the stack pointer? Because after I retrieve that one item from the stack, I better change the stack pointer so it goes to the next item that I will be ready to retrieve. So I have to use plus plus to reverse the operation of minus minus. The question is, am I going to put the plus plus before the typecast operation, or put it after the typecast operation?
The pre-decrement becomes post-decrement, yes, sir.
Exactly. It becomes like that. Okay? Now, the reason of this, why it is a post-increment, which means we make use of ESP or the value of ESP to do the indirect operation, and then we perform the plus plus operation, is because, by the way, what is the definition of ESP anyway? Look at it. Well, I scrolled that off the screen already. But for those of you who remember, it points to the lowest byte of whatever we just stored on the stack, right? So the pop operation is to retrieve the last item that we put on the stack into a variable in this case. So that means we do want to retrieve the item from where ESP points to begin with, but then after that we want to adjust the stack pointer so we'll be ready to retrieve the next item on the stack. So the plus plus is really basically saying, okay, this item is gone, now it is time to move to the next item. So the next pop operation would also retrieve the next item available on the stack. Okay. Let's take a look at the instructions to implement this one. So as a hint, we also have move long, add long, and then move long again. Okay. What do you think would be the order of doing these things? It's actually kind of like reading the other sequence backwards. Left becomes right, right becomes left, subtraction becomes addition. Yep, go ahead.
So would it be move long parentheses ESP into EX?
Uh-huh.
Then add L percent ESP dollar.
No, we are adding just 4 to ESP. Okay, so instead of subtracting 4 from ESP, which reserves space first, we are now adding 4 to the ESP because the 4 bytes that was pointed to by ESP is now retrieved. It is no longer useful on the stack. So I'm adding 4 to the stack pointer so to move past that point. Okay? And then what is the last operation? Yep. So it's almost exactly the opposite, okay? Both in terms of reversing the operand positions and also reversing the ordering of the instructions, and also changing subtraction to addition. So once again, do you think there's one single instruction that can do this using the I386 instruction set? Pop I, or pop long I, popple. Popple. So we have push out and popple. All right. It rhymes. Yeah. All right. So are there any questions about the push and pop instructions? Because I'm looking at it from the lowest level perspective first, and then I look at, okay, how do we implement that in assembly? And then we look at, okay, by the way, there's a shorthand to do it because we have a cisp processor that turns out to have instructions that can do all this stuff with one single instruction. Are there any questions regarding how to use the stack? No questions? Okay. On Thursday, I will have to give you guys a practice exam for the second exam, and then we'll have the exam on the Thursday after. Otherwise, it's final exam and 2 months
The final, we have the things from the final.
I just lost the file. I lost the file.
You lost a file.
I don't know.
This guy knows.
Oh, because and it doesn't go
Yeah, I know.
because when you do a dash code, you specify the open file, this is the open file for basically just white. When you use the command over wipes out
So you rename his alpha file to a source file?
not renaming.
Not gonna exit.
Oh,
So the command specifies the output file to be the source file that overwrote.
Is there a way to recover?
I don't think it's fine.
No, unfortunately, there's no way to recover the file.
Yeah, it could be.
No, mine would be reading over all if it weren't for the spacing. I need
Undo
to
it.
try and get
Nope. He overwrote the file.
Yeah, I did semi-script.
Well, the thing is because all the file is still contained in the journal, it's just not physically visible. You have to, there's a
No,
program.
because the background process has a lot of file operations already, you know, there's a very high chance that that cluster is already overwritten by something else.
Well, in the journal, but not on the actual one. You can. The thing is, you could probably recover an older version of the
What I
file.
couldn't figure it out is the files. Like I asked you, like I was trying to do 1, 2, 3, 4 instead of 0, 1, 2, 3.
Okay.
That was my problem. I couldn't figure that out.
You can recover an old version of the file using photo
You
records.
can probably redo it in an hour or less.
Work like a madman.
You could probably recover the file using photo rec, but that's like 4 hours because you'd have to let it recover the entire partition.
Well, he can probably rewrite it. Now that, but you already know the logic.
Yeah,
for the most
especially
part.
with what you went over today, that'll make it a lot easier.
You know what? You know, rewriting it, you know, may not be. It would kind of suck because I know you don't want to do it. But when you do it again, you know what? The second time you do it, different things will start to sink in.
And I'll probably do your thing so I don't have to do the return value or whatever, like combine the stacks that do just a while, basically, instead of a do well.
Yep.